The atom has discrete energy levels for its electrons. That was one of the first pieces of evidence for quantum mechanics. If you shine light through a gas, certain special discrete wavelengths of light are absorbed. Most of the others just pass right through. Or if you heat the gas up, it emits certain discrete levels of energy. What's that about? We now know it's because the electron wave function in the atom naturally settles into various discrete possible shapes. Those are the orbitals that you learned about in your chemistry class. The underlying equation is perfectly smooth and regular. The Schrodinger equation, the wave function itself, nothing discrete about it. There's no pixels, no lumps of anything, but the behavior turns out to be discrete. The miracle of quantum field theory is that particles are exactly the same kind of thing. Our 19th century physicists thought that particles were half the world and fields were the other half. Modern quantum field theorists knows it's fields all the way down. But if you look at fields vibrating, the quantum mechanical wave function of a field is just like the vibrating guitar string. There's a simplest way for it to vibrate, it's just empty space. Then there's a next highest energy level way for it to vibrate. We call that one particle. And there's other more energetic ways for the field to vibrate. That's 2 particles, 3 particles, and so forth. The world is not made of particles, according to quantum field theory. Particles are what you see. This is a real image of someone looking at particles. There's a cloud chamber with a magnetic field. You see tracks. All those tracks that you see in this picture are particles moving through the chamber. But really, the underlying mathematics is a smooth, continuous field that is constantly being measured, and you see that underlying discreteness. So I could easily spend the entire rest of the talk explaining that, but I took a vote. Some of you have know that I have a podcast called Mindscape. So I asked my listeners, my Patreon supporter listeners, to vote on what I should talk about. And they said, yeah, that's fine, but what we really care about is symmetry. And they're not wrong. That is an excellent choice for what to talk about, because what I'm going to try to convince you of for the rest of the talk is that symmetry plays an absolutely central, super duper important role in quantum field theory. It was already important in classical mechanics. It was pretty darn important in quantum mechanics of particles. But once you have field, symmetry becomes the central idea. I will, just a spoiler alert, I'll tell you one reason why. Symmetries explain all of the forces of nature in quantum field. You will leave this room understanding why that statement is. So what is a symmetry to a physicist or a mathematician? It's something you can do that makes no difference. I'm not talking about disaffected college students thinking nothing they do makes any difference or whatever. I'm talking about the mathematical idea of taking a system and transforming it in some way that leaves it in exactly the same kind of state that it was in when you started. So if I have an equilateral triangle, I can rotate it. If I rotate a triangle by 90 degrees, it does not look the same. That is not a symmetry. But if I rotate it by 180, it comes back to exactly where it started again. So this figure is from my book. I tried to take one of the most intimidating looking figures I could get. Don't like it when people say that there was false advertising there. This is what the book is about. We're going to mathematically think about how symmetry works. So you take the triangle in the top middle, you label it ABC on the corners, and then you ask, what can I do to it that changes it without making a difference? So one thing I can do is rotate clockwise by 120 degrees. I could rotate counterclockwise by 120 degrees. I can also reflect the triangle around a line that I draw from one vertex. There's a set of different transformations, and they can be combined in different fun ways. And now you have invented group theory. This is what mathematicians do when they think about how do we describe the kinds of symmetries there could be. And I don't want to distract you from the rest of the talk, but there's a set of transformations here. Each one of those triangles is separate, but what if it were a square? How many different ways could you change the square? Don't think about that now. Go home and you can think about that. But you can see how A little bit too much of this leads you to become a professional mathematician, and that would be a terrible thing. So this is a simple kind of symmetry. This is a discrete symmetry. Clicks on a dial, 1/3 of the way around in the circle. There's also smooth, continuous symmetry. And these become crucially important in field theory for a very simple reason. Imagine that I have several fields that are each have identical behavior. Okay, so remember, the field pervades all of space. It has a value everywhere. Now, there's different ways of characterizing what the field does. It will lead to particles. What is the mass of those particles? What are the interactions between that field and other fields? There's various characteristics that a field can have. How many components does it have? So imagine I have 3 fields that are exactly identical to each other. Let me label them: the red field, the blue field, the green field. This is poetic license. They're not really red, green, and blue, okay? You cannot look at them and see colors. That's just labels, completely arbitrary labels. And indeed, quarks have this feature. You might have told, depending on what street corners you hang out on, that quarks are either red, green, or blue. That's a tiny fib that you've been told, because it doesn't matter what you label the fields. And what that means is a quark can be halfway in between red and blue, or some weird combination of red, blue, and green. It's really a 3-dimensional space of vectors, red, green, blue space, or color space. And every quark has a direction. Every quark field, the up quark, the down quark, etc., they all have a direction in color space. Okay? And you could imagine other fields doing similar things. And then, since it didn't matter what we called red, what we called green, what we called blue, and since actual quarks are going to be some combination thereof, we could take those axes and we could rotate them a little bit. And still nothing would matter. Remember, a symmetry is something we can do that doesn't change anything. So rotating our axes, red, green, and blue axes in color space. This is not real physical space. This is not up, down, left, right, forward, backward, right? At every point, there are 3 fields, and we're rotating them into each other, not into directions of real space. And that initial choice of what to call red, what to call green, what to call blue was arbitrary. We could change it. I could use R, G, and B. Someone else uses R prime, G prime, B prime. The underlying physics is exactly the same. That's a symmetry. That symmetry is called SU3. The 3 is exactly the number of colors that we have here. There's other symmetries with different SU2, 5, whatever, okay? So that's nice. That's good when we have something like that, right? Mathematicians are happy. They can work out the theory of SU3, which is a group mathematically. Physicists are happy. They can sort of get a handle on what these 3 different fields are doing. But physicists are also never satisfied. They're like, okay, that's pretty good. That's a lot of symmetry. Like, you can rotate all these 3 fields into each other wherever I want. Okay. But I'm more ambitious than that. I want to rotate what I mean by red, green, and blue independently at every point in space-time. Maybe you can do that. Maybe you can. I mean, you can do that. Maybe it's a symmetry. Maybe it's not. Okay? If it were a symmetry, it would be an enormously bigger symmetry. The symmetry we were just talking about on the previous page, you can think of as a global symmetry. You rotate red, green, and blue once and for all throughout space. Here, this is what's called a local or gauge symmetry. You're separately rotating red, green, and blue at every point. And there's an infinite number of points in space-time. That's a lot of symmetry that you could have there. And you might say there's 2 sort of different ideas that are pulling you in different directions here. One is, why can't I do that? Who's to stop me? It looks like it might be a symmetry. You already told me it doesn't matter what's red, what's green, what's blue, which field is which. Why can't I choose that differently at different points? The answer is, you don't care what color the quark field is. That's just a label. But you do care whether the quark field at 2 different points has the same color or a different color. That's a physically relevant question. Indeed, inside a proton, you want the whole proton to be colorless. It's how they figured out there were 3 colors, because there are 3 quarks, and if you get 1 red, 1 green, 1 blue, they add up to white. But that means you need to be able to compare what the quark field's colors are at different points in space-time. But if I can change what I mean by the colors whimsically from point to point, that sounds hard to do. I need a way of comparing what the color of a quark is at one point in space and another one. You'll be unsurprised to learn that what that means is you need another field. So you have the quark field. Sometimes the physicists will think about, like, there's 3 quark fields because there's 3 colors. Sometimes they'll just call it 1 quark field with 3 colors. That's completely because they know what they're doing. You are expected to follow along. But there's a quark field, or a set of them. And then you need an extra field in addition to the quarks to help you compare what the colors are doing from place to place. That is called a connection, or a gauge field. This is the most abstract and conceptual we're getting tonight, okay? You got to get this. This is not optional. You have to get this. To make it a little bit more graspable, here's an analogy which is like 98% good analogy, okay? The connection is in some sense telling you what it means to keep a vector constant. In this case, the vector is the quark color, okay? If we wanted to keep that constant from place to place, how would we know how to do that? That's what the connection is telling you. It's much like a waiter who's gotten unlucky enough to be working at a restaurant in Switzerland where the terrain is very hilly, and they're trying to carry a platter, a tray, with some wine glasses and a bottle on it, and they want to keep them vertical. They should watch where they're going, but their customers are calling and the manager is yelling at them, so they have in their mind a perfect map of all the hills and valleys that they have to walk through to get to their tables. That's what lets them adjust the tray so as not to spill the drinks. That information is a connection. How to keep a vector constant, in this case, how to keep the wine bottle pointing vertically with the tray horizontal as you move up and down across these hills. That's an example of a connection field, the knowledge of how the hills are going up and down. And there's a hint, this is why it's a pretty good analogy, of something else going on here. Because you know that if you stand on a hill, or if you have a bowling ball that you set down on a hill, there's a force that pushes the bowling ball down to the bottom of the valley, or pushes you if you roll on the hill, right? So it's almost like the undulations, the slope, the curvature of the connection field gives rise to a force. And that's true. It's exactly true. That's going to be the punchline. All the forces of nature are like that. All the forces of nature that we know of come from curvature of gauge field. That's why it's worth thinking about these symmetries.